Welcome to Lecture 5.3c. In this video, you're finally going to learn the real way to calculate definite integrals, which is by using something called the antiderivative. But before I can explain anti-differentiation, I need to briefly remind you of some of the other things we've been building up. We started this unit talking about the area under the curve, and we came up with this idea of using rectangles to estimate the area under the curve. At that point, this was just kind of an intellectual challenge. Is there a good way to do this? Sure. After that, we developed some notation for something called a Riemann sum, which allowed us to talk about making these rectangles smaller and smaller and smaller so that the estimate would be more and more accurate. From there, we realized that if we want the exact area under the curve, we could use something called a definite integral, which is basically the limit of the Riemann sums as the size of the rectangles gets smaller and smaller and smaller. Now that solution was really a very creative, brilliant one, and I know you guys were all particularly excited to be doing limits again, but the truth is trying to calculate the limit of the Riemann sums is a fairly tedious way to get the area under a curve, which seems like it should be a pretty simple question. In the last video, we talked about some properties of area under the curve, and those properties will hold true if we have an exact way of calculating that area. Today's video is going to show you exactly how to find the area under that curve. And the trick to understanding it is actually to think about the area under the curve in terms of what it really means, not just as an abstract mathematical question, but as a question that we face every time we talk about rates. So, in this example, if each of these rectangles is measuring a sliver of area underneath the curve of the rate at which the water is flowing over the waterfall, we've already discussed that one of these rectangles' area really is a representation of how much water went into the pool at that particular interval of time. So if I add up all of the areas, I end up with the total amount of water that flowed into or possibly out of the pool. In other words, it's the total change in the amount of water. So if this function is the rate at which water is flowing, we think of this function as a derivative of that other function that actually tells me how much water there is. That idea is where we start in order to understand antiderivatives. By the end of this video, you should be able to identify antiderivatives and use them to evaluate definite integrals. But I want to start with that core idea, not just because it's an important piece of calculus, which is this incredible accomplishment that humans have invented, but also because understanding this idea at the basis will help you find antiderivatives much more reliably. So here's a curve, and we've got some area underneath this curve highlighted. If we think about this curve as a derivative function, maybe even as a velocity function, the area of the shaded region should represent the total change in the position graph. In other words, if we think about this as a derivative function, there's some other function whose derivative this is. What could you infer about that original function's graph based on what you see here and this curve? Right, we can actually assume quite a lot. We know that that original function must start out increasing because the derivative starts out positive. And then it must have a maximum somewhere close to negative 0.8. And then the original function must be decreasing this whole middle time. It must have a minimum somewhere around 2.8, and then it continues increasing towards the end. That being said, we don't know exactly what the function's going to look like unless we have an actual function rule. So if I told you that this original parabola was the parabola x squared minus 2x minus 2, and we wanted to figure out what other function's derivative this is, we could come up with an actual equation using kind of the same logic that you used on one of our earlier exams. It's kind of like taking a derivative backwards. In fact, that's exactly what an antiderivative is. It's a function whose derivative is the function that you started with. Now there's two really important things you need to know about antiderivatives. The first is that an antiderivative is a function. It's not a number, it's not a slope value, it's not an area amount, it's a function. The second thing you must know about antiderivatives is that every function has an infinite number of antiderivatives. Unlike taking a derivative, there's only one derivative for any function. Taking an antiderivative means that you have lots of possible answers. Look at these three examples. These are all antiderivatives of the blue function. What do these functions have in common? Exactly, they are exactly the same in all of the terms that have x's, and they only differ by this last constant. In fact, that's going to be true for all antiderivatives. You also probably notice that if you take the derivative of each of these terms, you get the blue function back. That's the whole point. Let's try this. It's pretty simple. For each of these 8 functions, your job is to find an antiderivative. Remember that there are multiple correct answers, so I'll model the first one and I'll show you how you can kind of convey all of the possibilities just by writing one equation. So normally when we write the antiderivative, we're going to label it with a large f. Little f is the function you start with. We used to use f and f prime, but in this context, we're not going to use the prime notation necessarily. You just need to know that the big F is the original function for which the derivative is the function we have at the top. When I do this, oftentimes it's quickest just to do like a little guess and check in your head. So think about trying to end up with an x to the 5th. Well, from what you know about derivatives, when you have polynomial functions, the exponent always drops 1 when you take the derivative. So I must have started with an x to the 6th power in order to end up with x to the 5th. Similarly, my second term must have started with x to the 3rd power in order to then end up at x squared. Notice it's really the opposite thinking. Now, as guesses go, this is not a bad guess, but think about what the derivative of this function would be if I left it just as is. The derivative of x to the 6th would be 6x to the 5th, and I don't see a 6 out front. So what I want to do is I want to put a coefficient in front that will somehow, quote, cancel out that 6. In other words, if I put the fraction 1/6 out front and then multiply 6 times 1/6, we're actually going to end up with x to the 5th times 1. And that factor kind of adjusts my coefficient. For the second term, if I take the derivative of x cubed, I get 3x squared, and so that's all right just as it is. There's no adjustment that I need to make. Remember that when you take a derivative, the derivative of any constant like 5 or 2 would be 0. In other words, I can add any number I want to the end of this antiderivative and have it be a perfectly good antiderivative. So instead of picking a number randomly, you should end all of your antiderivatives with a plus c. On your quiz, if you don't include that plus c, you will not receive full credit. An antiderivative always has this factor at the end, which we think of as being any number we want. So that's the antiderivative for number 1. Go ahead and work out the remaining 7. So you probably saw these answers in Edpuzzle as you went through and solved them all out. A couple notes: a lot of people will have struggled with 4 and 6. Both of these are ones that you can rewrite as exponents, x to the 1/2 power, x to the -2 power, and that's usually your best bet for thinking about how to find the derivative. Other than that, they're really the same as the first 3. For 3, you probably wanted to distribute before finding the antiderivative. And then 5 and 7 are really just about remembering important derivatives. It's really important to remember the derivative of ln is 1 over x, so the opposite, the antiderivative of 1 over x, is just ln, and that's just a memory thing. 8 is a memory thing as well, remembering that e to the x is its own derivative, and there's actually a little chain rule thing going on. If you got any of these wrong, it's really important that you stop now and go back to double check why the antiderivative, if you take its derivative, gives you the original function back. Great, so now that you're comfortable with antiderivatives, they're kind of like puzzles, they're kind of fun, they should be quick. Why do we care about antiderivatives? Well, this is this big idea I keep trying to come back to. When you try and evaluate the integral of a function on a certain interval, from a to b for example, the meaning of this expression is the area under the curve, But it's this very interesting fact that the area under the curve of this function is the same thing as the net change in this other function, the antiderivative. So this relationship, which we've kind of been intuitive about, is actually a really important result called the fundamental theorem of calculus. And it's used to evaluate a definite integral. Let me show you an example, and this will all make a little more sense. Suppose we want to find the integral from 1 to 3 of 4x minus 3x squared. I understand that this is really asking me to find the area under the curve from 1 to 3 under this function. The first step to evaluating this numerically, not just estimating it using a Riemann sum, is to identify what the function's curve is and to find an antiderivative. So we would say the curve in question is f of x equals 4x minus 3x squared, which has an antiderivative of 2x squared minus x cubed plus c, where c could be any number. The fundamental theorem of calculus says, since I can find an antiderivative for the curve inside the integral, the definite integral from 1 to 3 must equal the net change in the antiderivative function. In other words, if I plug 3 in to the antiderivative and subtract what I get from plugging 1 into the antiderivative, that will be my numerical answer for the area under this curve. That's a piece of cake. All I need to do is plug in 3 and 1 and then simplify. And when I do that, you'll see always that the c's cancel out and they end up with, in this case, a numerical answer of 8, which represents both the change in the antiderivative function from 1 to 3 and the area under the derivative function's curve. 8 is the answer to this definite integral. In a second, I'm going to have you work a bunch of examples that look just like this one. Make sure that you understand the steps that I took. This at the bottom is kind of like your scratch work, but when you do this in your quiz, I'll expect to see the antiderivative clearly labeled. Before I give you your practice problems, however, I just want to refer you to a YouTube video. This YouTube video, which I'm not actually going to play right now, will help you learn how to use your graphing calculator to evaluate a definite integral. The link is going to appear in the side of Edpuzzle, and it's your job to click that link and watch the YouTube video before you do the practice problems at the end of this video. It's very quick. It's just 4 minutes. It's very clear. He shows you the buttons to press. As you can see here, it involves Math 9, and it should be pretty self-explanatory. I'm just flipping through it here. There's 2 different methods. But being able to do this not only is going to help you check your work in this video, it's going to be really, really helpful for you on your quiz. So don't neglect the YouTube link. It's on the side of your Edpuzzle. Great, so to end today, you've got 4 examples for you to work out. This last one, which is covered by the Prezi symbol, says the integral from -1 to 0. For each of these 4 examples, your work should look exactly like the work that I did a minute ago. It looked like this. Your job is to find the antiderivative and use it to evaluate the integral. And then you can check your work using the calculator skill that you just learned from YouTube. Nice work. That ends today's video. And as a reminder, this is the end of your February break homework. So by class on Monday, you should be comfortable finding antiderivatives, using them to evaluate definite integrals, and then you should also understand all the material from the last 2 videos, which were about using properties of integration. Nice work. I'll see you in class.